All right, so thanks everybody for joining here today. We're starting to get towards the end of the semester. Just 1 week until last day of classes and then reading day, and then on to exams. So thanks everybody for joining here today. This is the last seminar or Space VT seminar for the semester. And actually, I just today got somebody who's looking to do one actually for next semester already. So that'll be fun. I'll start setting up the schedule for that though. Not now, sometime in the next probably a month or so. But today we have the InspireFly team. I think this is record attendance with the whole team here for the seminar. So thanks for filling the room. Without any kind of more delay, I'll turn it over to you.
Thank you. So hi everyone. Thank you all for being here this afternoon. So my name is Matt Glancy. I'm a senior in mechanical engineering and I'm the project manager for InspireFly. Go to the next slide. So the first thing on today's agenda is I'm going to go through a quick team overview, talk a little about what we're all about and a little bit about our team structure. After that, I'll pass the mic to Austin Moore, our chief engineer, where he'll go through our mission overview. And then following that, we'll go through a little deep dive into our 3 engineering sub-teams, which are mission ops, payload and electronics, and mechanical systems. So starting off with our team overview, our team slogan is "Put your face in space." Our mission is to develop a novel 1U CubeSat, which presents a unique style of access to space to the general public. And the way we're going to accomplish this is by attaching an external display screen to the side of our CubeSat, and it's going to have a camera facing the screen, which is attached to a deployable boom system. And the idea is that we'll be able to uplink photos of ourselves to the screen and essentially take photos of ourselves in space with Earth in the background. So InspireFly was founded in 2018 by Virginia Tech alumni Ben Strickler and Simran Singh. And in 2018, the founders participated in an annual Space Vision conference in which they won a fully funded launch with NanoRacks and Astratus. And so all that's left to do now is build the satellite. Next slide. As I mentioned, we are an undergraduate team comprised of around 30 members distributed amongst our 3 engineering sub-teams, which, as I mentioned earlier, are mission ops, payload and electronics, and mechanical systems. And we'll go a little deeper into all of these sub-teams following the mission overview. On top of that, we're also advised by faculty members Dr. Kevin Schroeder, Dr. Samantha Kenyon, and former InspireFly member and current Virginia Tech grad student Richard Gibbons, who is actually joining us here today.
Hello.
And so there's also a 3D rendering of what our CubeSat will look like with Earth in the background, as shown here. So how are we funding our mission? So in previous years, we've had some troubles with funding, but we took a major pivot this semester when the AMP lab with the Z department decided to actually help us out and fund most of our electronics for us. And so that alleviated much of the funding struggles that we were facing. We still have to purchase our chassis and our solar panels, but regardless, this has definitely alleviated much of our troubles. We also raise money through crowdfunding efforts, selling merchandise, and applying for grants. So I'll now pass the mic to our chief engineer, Austin Moore, and he'll go through our mission overview.
Sweet. Thank you, Matt. Hello, my name is Austin Moore. I'm the chief engineer for InspireFly, and I'm also I'm a senior this year in aerospace engineering, looking to go into the space field. So what you see here is ContentCube, which is our CubeSat design. The point of view that we are is the camera's point of view, aiming at the CubeSat with Earth oriented in the background. We have a bit of an outdated image there shown on the CubeSat, but that's a bunch of our old leads, so a little reference to the past. But this is basically our concept. So what it's going to be is you're going to uplink an image from the Virginia Tech ground station to the CubeSat. The CubeSat's going to show it on the screen and then autonomously take a picture of that screen. And then the image that the camera takes is going to be downlinked back to the ground station so that we can save it and share it with whichever group wanted the picture taken. So these are some of our mission objectives here. Number one is to develop a 1U CubeSat with a unique and novel payload encompassing an external display screen and a camera. The second objective is to uplink an image to the external display screen from the Virginia Tech ground station. The third objective is to use active ADAX to downlink an image of the display screen with Earth in the background. The fourth objective is to operate in orbit for at least 6 months. And the final and arguably most important objective is to verify the validity of the external display screen in the space environment. We are one of few teams that's actually working on this technology to kind of test it out. And if our tests go well, the external display screens could be used in all sorts of different instances, such as on the sleeve of an astronaut's suit, so that you could use it for communications or data, or screens on the outside of space stations that could also be used for data and quick, easy access. So up next, we have our requirements. These all need to be completed for us to have a successful mission. So the first requirement is that ContentCube should have an external display screen on the satellite. The second requirement is that the satellite shall contain a deployable boom system. This is so that we'd actually be able to film the external display screen. The third requirement is that ContentCube shall contain a radio capable of connecting with the ground station at Virginia Tech. The fourth one being the CubeSat shall meet the CubeSat requirements for a 1U form factor set forth by NanoRacks as per Strange's request. This is just so that we would be able to fit into the deployer that they have already built, and we don't have any issues with that interference. And then the final one is that the satellite should conform to NASA's standard materials and process requirements for spacecraft, just so we don't get into any legal issues and don't have any issues with space debris. So what you're seeing here is our ConOps for our mission. As previously stated, we've won a launch on a Falcon 9, so the launch is fully funded. And that's actually scheduled for about Q1 of 2024, hoping to hit that deadline. So after launch, it'll move on to main engine cutoff or MECO, followed by stage 1 separation and fairing separation, basically as soon as we get out of the atmosphere. Following that, we have stage 2 ignition, orbital insertion, and ISS rendezvous. Once we're on the ISS, the astronauts on board will place us into the orbital insertion device and will actually deploy us once they go to reset their orbit. When they go to move, they're going to jettison us along with about 10 other CubeSats into the current orbit. After we leave the ISS, we have about a 30-minute wait time just to make sure we're not going to interfere with any other satellites and that we have enough distance safely from the ISS before we go to initial power-ups and health checks. Once everything is healthy, we're going to go to boom deployment and solar array deployment and start working on the detumble to get us oriented the way we need, followed by a payload system check just to make sure that everything's running nominally. And once we're sure that everything is working and the way we want it to be, we move on to start our mission, where we'll take the photos and downlink to the ground station, where it will be received at the Virginia Tech ground station. And then this is some of the mission overview here. We have an estimated mission cost of $25,000, which includes a engineering model, a flight model, and about a 20% margin, just for any errors that could come. We have a 5-year turnaround from initiation to handoff with an estimated launch date of Q1 of 2024. As previously stated, we are an undergraduate team advised by Dr. Schroeder, Dr. Kenyon, and Richard Gibbons, who's again with us. We have a couple industry mentors, namely Cole Winkler from Astranis, who's been helping us through the radio licensing and any forms and documents that we need to fill out. He's been helping us with those just to make sure we get everything right. Along with Michael Pham, who works for Bronco Space, and they've been helping us a good bit with the design. So any questions that we have regarding space or where we're going to be able to fit certain things into, which will come up later, but ADAX is an issue for us, trying to fit, get sizing in there and trying to have the space. Michael's going to be helping us a good bit with that. And then below, we have a couple conferences that we've been able to attend. So it's Space Vision 2019, IAA 2020, and PSW 2020. So with that, we're going to move on to sub-team overviews and recent progress. Starting first with the mission ops team, where Yuri is going to give his talk.
All right, hi everyone. My name is Yuri. I'm a senior in aerospace engineering, and I'm one of the 2 mission operations lead co-leads. So I'll start by introducing our basic orbital parameters. Because we're being deployed from the ISS, our trajectory isn't going to be far off from that. And so we've been using those parameters to kind of do preliminary analyses on our satellite. Well, we can move on to the next slide. This isn't exactly too exciting. Now, our on-orbit operations. On the left, we have a more visual representation of what our orbital parameters are going to look like. And it's a fairly generic or traditional LEO orbit where we'll be seeing about 57 minutes of sunlight and be eclipsing for about 35. And over the course of a day, we're hoping to have about 7 access times to our ground station here in Blacksburg, which should give us more than enough opportunities to do satellite health checks and uplink and downlink pictures. With those opportunities, it'd be nice to see how many people get involved, send a lot of pictures, get more exposure for everyone. So this is our finite state machine. We won't get too detailed in this. As far as CubeSat missions go, it follows a fairly similar setup. We have a detumbling mode, tumbling mode, communications, power mode, as well as all the usual safety modes. Where our project becomes a little more unique is our picture taking mode. So unlike like a remote sensing satellite or something, we don't want to be facing straight at Earth. You saw the picture that Austin introduced earlier on, where we want to try to get the horizon to give pretty pictures for everyone who wants to be on top of it. So one of the challenges we're looking at here is our pointing requirements, which we're actually working on right now. And that's where the ADAX conversation came up. The challenges we're seeing with the 1U CubeSat is really the sizing, and having a boom and a camera on it kind of limits our space for the ADAX systems. So we've been playing with the idea of seeing if we can pull off a only magnetorquer system. That's not going to come down to what the pointing requirements tell us, if it's doable or not. And if it's not, then we're going to get creative and we're going to see how we can solve that problem. So I'll pass it on to Willie now. Thank you.
Hey, how's it going? My name is William Supa. I'm also a senior aerospace student and one of the co-leads of the mission ops team. So something that we're actually working on right now is creating a detailed link budget for our spacecraft. So what I've shown here is actually an STK access report from the ground station at Virginia Tech. So we have a couple passes each day, and so each pass will have approximately about 10 minutes to uplink and downlink. We've also done some environmental analysis. So what you're actually seeing on your screen here is some radiation simulations run in STK and SPENVIS using 2 different models. So we've actually done these for solar minimum and solar maximum, just in order to fully define our environment. Next, we also have run some thermal simulations. So this is actually a thermal simulation run using a code created by a grad student named Nicholas Jones. With some tweaks from us, we actually ran this code for both a cloud coverage percentage of 0 and a cloud coverage percentage of 100. Following our codes and our models received, all of the data was then imported into an ANSYS simulation. So this is actually an ANSYS simulation that we had done previously. This is not the current state of our CubeSat. This was a previous model, but this does give a little bit of what we were working on with our thermal simulations previously. But now I'll actually pass it on to Joe and the payload and electronics team.
Hi, my name is Joe. I'm a junior in electrical engineering, and I'm one of 2 sub-team leads for payload and electronics. The other member could not make it today. So on a broad overview, payload and electronics is in charge of everything electrical on the satellite. We are designing and constructing all of the required PCB boards. Current plan is to have 4 total boards, 1 that handles the payload, 1 that handles all things power, 1 for the onboard computer / radio, and 1 for the ADAX system. Next slide, please. So here's a very top level view or block diagram of the plan on how this will all be laid out. The power system will be powering the payload, ADAX radio, and onboard computer. Additionally, the onboard computer will be able to monitor the health of the power system. And with that information, the onboard computer will be in charge of turning off the payload, ADAX, and radio systems as needed in order to ensure mission success. And then due to the time constraints of this project, we have decided to use primarily open source CubeSat designs as our basis, as we don't have the time to design everything by hand. Given this, the payload board has to be entirely unique, as our payload is entirely unique. However, the power, onboard computer, radio, and ADAC system are all being modeled after open source designs. So starting with the payload PCB will be responsible for the monitor, camera, and boom deployment. The current camera we are working with is the Eximia camera. The current display monitor we're working with is a Adafruit OLED monitor. We are looking into different monitors due to this current monitor being smaller than we would like to use. And then further onto the payload, we have tested the angle of view and focal length of the camera to determine the best lens, and also to determine the distance that we need our arm deployment to be in order to maximize image quality while also minimizing the size of the boom deployment. And then once we have our payload PCB built, we will move on to thermal and pressure testing. Then the block diagram of the payload. The idea is to have both the camera and display screen be talking to a local computer that just handles things on the payload board. This local computer will be talking with electrically erasable programmable read-only memory. This will be used to tell the display screen what to display. Then additionally, there will be flash memory on there for more long-term storage. This will be where the pictures are stored so that we can downlink them back to Earth. Then moving on to the power system. The power system is based on the open source CubeSat FloripaSat 1. This design was chosen for its modularity, and also out of all the open source CubeSats, the FloripaSat was the best documented, which made it very easy to modify. However, given this, we are currently in the process of sourcing replacement parts, as this design is about 5 years old, so all the parts used are out of stock. Then moving on to a block diagram of the power system. Starting on the left-hand side, we have a solar panel that feeds into a current sensor. This current sensor will be talking to the onboard computer, so we can measure health requirements. The same also applies to that voltage measurement. Then this will hit a boost converter. Then everything to the left of that central dash line will be repeated for each solar panel we have. All of the solar panel's voltage and currents will be combined. We'll get one additional voltage measurement of that total voltage before it passes through a kill switch. This kill switch is here in case anything goes wrong with the solar panels. We can disconnect them from the rest of the circuit. Then after this, it'll feed into the battery board where we can charge our battery. We will have an additional device to measure the voltage so that we know how much voltage we can pass to the rest of the boards. Then finally, for each additional board, being the ADACs, onboard computer, radio, and payload, we will have an additional DC to DC converter so that we can supply a steady voltage and current to each board. Then moving on to the onboard computer, we're once again basing this on the open source design FloripaSat 1. We're once again sourcing available components. However, we have to modify the design to incorporate a radio onto their PCB board. And then a block diagram of the onboard computer / radio. Starting on the left-hand side, we have the onboard computer. This will be sending and receiving data from the power board, payload board, and ADACs board, in addition to flash memory, so that the onboard computer can properly monitor and control the rest of the satellite. Then on the right-hand side is the radio. Radio will be communicating with either UART or I2C, dependent on what is easiest once we have things more ironed out. And then, so yeah, everything on the right-hand side is the radio. And the next slide, please. And then the reason why the radio was so well defined was because the radio itself is based on the open source Little Free Radio. This design was chosen as it met all the communication requirements, and also it was very well documented. As you can see, they provided a very nice block diagram for me to steal. And once again, we are currently updating the schematics with available parts, as this design is a few years old and the parts they used are no longer in stock. And then finally onto the ADAC system. This is the most up in the air at the currently. It's currently being based on the open source ORSAT satellite. This satellite was chosen as their ADAC system includes both magnetorquers and reaction wheels. However, once we have more information on the pointing requirements, we can hopefully gut the reaction wheels, as they are very large and will be very difficult to fit onto our CubeSat. And then more ambitiously, we could take out the magnetorquers as well if we can figure out a way to get the desired pictures without having any sort of 8X system. And I'll pass it on to Ryan with mechanical systems.
Hi, my name is Ryan Thier. I am the sub-team lead for mechanical systems, and I'm currently a senior in aerospace engineering. And I'll give you guys a brief overview of what mechanical systems does. So for our mission for this project, we want to ensure that the camera is going to be deployed successfully and be able to make sure that we're able to establish the connection the camera with the camera and the CubeSat itself, and also to make sure that we're able to project the picture that we're hoping for. We also want to make sure that our boom deployers can be able to fit within our 1U CubeSat. Essentially, a 1U CubeSat, there's not a lot of volume given the space of hardware that's going to be implemented. So we want to make sure minimization is as much as possible. So some of the challenges that go with MS is, what designs are we looking for with our boom deployer? So our team was able to brainstorm numerous different designs, such as we're going to be able to use gas as one of our deployment systems. We could be able to use a wraparound tape screen, or we could even use like a telescopic boom. And actually, the previous two boom deployments will be mentioned later on, and we will show why that we have not used that and actually move on to a different design. Another challenge is, given the amount of space, will it be able to deploy the way that we want it to? It is a big challenge, as mentioned before. 1U CubeSat, there's not a lot of volume, and minimization is really going to be the key for this. And the final is, will it be able to operate in harsh conditions? We also want to make sure that we want to be able to count the harsh environment that's going to be presented in outer space. And essentially, we want to see that our boom deployment does not fail given those outside environment issues. As mentioned before, we have our previous boom designs that have been presented throughout the lifetime of InspireFly. And the left you see is what we call a wraparound tape screen. Essentially, you can see with the black tape that is wrapped around the CubeSat itself. And along the end, there's going to be a camera that is attached to it, and it's actually fitted into a slot in the CubeSat. What is actually attached to this tape screen is a wire that is essentially going to be burned off through a mechanism called burn wire mechanism, which there will be a nichrome wire attached to this wire, and given enough power, this wire will be able to cut through the wire, and essentially the tape screen will be able to unravel itself and obtain full deployment. And to the right was the telescopic boom that was mentioned earlier. This was going to be made out of aluminum, and essentially it's just the same configuration as the telescope, but it's going to contain torsional springs that are going to be placed inside of it. Once it's inside the CubeSat, it would have been compressed to the amount, the shortest span as possible, and once it's deployed, it's going to be able to deploy out and give it the camera. And I'll show in the next slide, it's going to be videos of deployments, and which will contribute to the reasons why we're sort of uncertain of the use of their deployment. So these are going to be like simultaneous. So the one in the left is essentially going to be like a little idea of what the wraparound tape screen deployment would have looked like. And essentially, a lot of force is going to be generated into the CubeSat. And the fear is that this would mess up our orientation along the low Earth orbit, and we would not be able to generate the picture that's going to be produced. And along the right side is going to be the telescopic boom. Although the deployment is more susceptible compared to the wraparound tape screen, the only issue is the wraparound telescopic boom, essentially is the size of it is not going to be able to fit within the given area that's going to be presented for our 1U CubeSat. And also the issue is the phenomenon that is found in space is called cold welding. Essentially, when two metals come into contact, it was able to weld itself without the need of heat. So that could be an issue for deployment. And then for our current boom design, I was honored to meet with one of the ProSat members, Minza, and essentially he was able to go about the design using a parabolic bistable tape screen that's going to be deployed using a passive deployment system, and that can be reeled back using a servo motor. Our idea right now is to be able to minimize what was needed from this design. Since our project only requires us to deploy, we could be able to get rid of a step motor that is used for retraction. And based on the size, the parabolic bistable tape screen that we could be able to obtain, we could be able to minimize the size of the deployment system itself. So once we are able to obtain our current boom deployment mechanism and be able to produce prototypes, we have 4 different tests that we want to try out. The first one is the deployment test, and essentially, as what is by its name, is we're going to test the deployment system and see if they're able to be operational. One of the issues is that we get to account for the 1G gravity that is presented in Earth. So essentially, we're going to deploy in different orientations to see that the effect of gravity is not influencing the deployment system. We also want to be able to determine the amount of force that is going to be exerted along the CubeSat. The next 2 are going to work with testing along how the CubeSat is going to be interactive with the harsh environments within the space itself. So we want to be able to test this deployment within the heat or cold and see if no failures have been occurred. Finally, we want to lay out future plans. We want to be able to calculate the moment of inertia and center of gravity within our CubeSat between both the stowed and deployment configuration. We also want to minimize the boom as much as possible and be able to determine the amount of length required for our camera to be able to obtain the picture that we hope for. We're going to also construct prototypes for testing. Later down the line, we're also going to determine how we're going to be able to connect with our camera. That's going to be attached with the boom. So that's going to be a big challenge. And at the end, we're going to be able to produce flight-worthy models and be able to proceed with the mission as planned. And hopefully success comes out of this.
Yeah, so thanks again, everybody, for joining us today. We're very excited for the opportunity to tell you a little bit about our team and our mission. We'll now open up the floor for any questions.
Yeah. Maybe I'll start. One thing I was going to ask is, with the attitude system, have you thought about doing any kind of like passive attitude, which is a really fancy way of saying like putting a magnet on the CubeSat, and then as it goes through the Earth's magnetic field, it tries to line up?
So I guess we haven't gone that passive. The lowest we've gone would be just simply using magnet torquers and still putting a little bit of electrical current through there so that we still have some pointing ability. It might not be 3-axis, but it gives us an ability to kind of recover certain things if something starts to, especially for detumbling. So once we figure out how strong the point is going to be, if we can do it with just a magnet, that would be ideal, save us some space. That's still in the works.
Yeah.
Thank you.
Any other questions?
I was great job, by the way. This is really interesting. Could you guys say a little more on why the microprocessor and the communication system are on the same board? I would have thought that would generate a lot of heat that you'd have to deal with.
So the reason we decided to put the radio and microprocessor on the same board is due to the space requirements. Is we already have the battery board, which is pretty big in it of itself. We have the payload board, which we want to essentially have a blank check for how much space that needs. And then that leaves us with a fairly limited amount of space to put the main microprocessor, the radio, and the ADAC system. The ADAC system is probably also going to take up a lot of space. So we've been forced to essentially put the main microprocessor on and the radio on the same board, as that's the only spot we really have to save space.
Okay. Have you done the calculations to see if there's any problem doing that?
We haven't looked into the heat problems with that yet, but we will make sure to do that in the future.
Okay. And then I was curious on the boom. Interesting problem you have, all the considerations you have figuring out what's the best way. I was wondering if, you're worried about putting torque on a spacecraft when you eject the boom if you do it too hard, but if you have something that's super reliable, could you just have sort of a duplicate that's not extending the boom as big, but something with the same moment of inertia in the opposite direction? That way you cancel each other out and you don't get such a big jerk. Is that something you could do to alleviate your concern?
Yeah, that is a viable option, really, Nancy. But I think for us, it's like for the boom, there's essentially not a lot of space, Nancy, and then we also got to determine how much power it's going to use based on our small CubeSat, Nancy. But that could be something that could be really into consideration. And essentially, once we minimize this first deployment, this first boom deployer, we could be able to determine how much free space is going to be made. If we essentially have half of the space that's available that's going to be used with the boom deployer, and then we have an extra another just about the same amount of size as available, That could be a viable option, really.
Okay, I think the second one can be a lot smaller. All you need is the moment of inertia to be the same, not the length or anything like that.
Yeah.
But I think if springs are the main method, right, there's nothing more reliable than that, right? Then you don't have to worry about power. You can just put some sort of I don't know, either a paraffin actuator or some sort of bolt cutter. So you just give it a little current and then it'll release the springs. I think you have the right idea. Reliability should be your number one thing, and then you can deal with whatever else comes up somehow.
That's a good question, though, too. We'll look more into that now, too. And essentially that is actually like simplifying design a lot now, too. And I think we're all aiming for simplification, so that would be really good to brainstorm with.
Okay. And one last, the monitor you're using looked interesting. I mean, it's meant for that kind of environment. It looks pretty rugged.
My other team lead, he's been more in charge of the payload side of things, specifically the monitor. I believe we've determined it can work in space, but the specifics of that I'm not sure of.
Okay, just something I'm curious about. It looked super rugged, so I was wondering what the background, what it's really intended for.
I can talk a little bit on this too. I was previously on this team before I came up to chief engineer, working on payload, and we do have two other options that we're looking at as well that would be less rugged. Our main thing is once we get access to a thermal vacuum chamber, we're going to see if any of these screens will actually be able to hold up in that vacuum. And that along with the heat are some of the main considerations that we're going to have to worry about through testing.
Okay. Could I make the suggestion that you actually don't start with it that way? The problem is if you have a material and you're testing it that way to see if it survives in vacuum, what's happening is it's outgassing, right? It's coming apart, right? Where does that stuff go? It's going to go on the surface of the vacuum chamber. So you don't want to put it in the vacuum chamber unless you have some reason to believe it's not going to damage the vacuum chamber. If you're worried that it might outgas and come apart, that's pretty risky. You should be able to do a search on the materials, whatever adhesives are in that, the material that's on the surface of that screen, all those sorts of things. That should be something you can research and find out what their outgassing properties are. You know what I'm saying? You don't want to paint the inside of the vacuum chamber.
Okay, sounds good. Yeah, we completely understand. We'll go into that research a little bit before we do any vacuum chamber testing.
Okay. Sorry, so many questions. I'm very interested. Looks like you guys are doing a great job.
I think those are great questions, and certainly some great kind of things to think about. One other thing I think they hadn't really covered. Has anybody looked into? I know you did like a solar mid, solar max, and I know this relates to it. Of what's the expected orbit or lifetime of the satellite? And maybe I missed that or something. Yeah, up there.
Sure.
Yeah.
I guess if you.
No, I was just gonna say, all of our simulations were run, for radiation, were for 2 years. We were following the NASA JPL radiation design factor for that.
Okay.
So it's kind of expected about 1 year, but we did say that as long as it lasts 6 months in orbit, that's kind of our goal. So we haven't done any simulations to see how long the orbit and talking about the orbit decay or anything like that. But that is something that we will look on to in the future.
Cool. 6 months. 6 months to 2 years is roughly. Yeah.
What is limiting the lifetime? Is it decay of the orbit or your electronics?
Yeah, so I think for that requirement, I think that NASA is now putting in a new standard that all spacecraft have to come out of orbit within about 5 years. So I think that's part of what they're trying to do, is trying to mitigate space debris.
Okay, so 6 months it'll fall out of orbit. The expectation. Yeah, a couple simple questions. The power part of the solar panel. how does that work? The solar panel is not being directed to face the sun. Or is it always maintain its orientation to the sun, or is it just taking advantage of whatever sunlight there is?
So, or I believe that's part of that's to be determined if we want to have like a solar panel on each face or deployable solar panels. But the idea is we're going to have more than one, and with the voltage and current measures, we'll be able to determine which solar panel is being hit with sunlight. Then from that, depending on our ADAC system, be able to potentially maximize the amount of sunlight we're getting at any given point.
Yeah, so that the SDK like day in the life thing was on that was more of, so it should be mentioned that we are going through a major redesign process right now. So we actually switched our provider. We were going to use a Kratos bus, and that originally came fully stocked. But we are switching more to our own design and doing a little bit more design ourselves, as well as purchasing some parts from Bronco Space, just because it is a little bit cheaper to do it that way. So originally we did have in our mission plan that it would face the sun, and so those original models were that it was going to face the sun whenever we had that time. But I don't think it's been fully discussed with our new bus and how we want to do that.
And the battery that you feed, what's the capacity and how heavy is it? Yeah, you may not have decided.
That is
yet,
a
but
good question. I do not know off the top of my head.
So very preliminarily, just from what we've seen from what Bronco Space has provided us, they have, I couldn't get any specifications on it. It was purely visual, but it took up a lot of space. They seemed very big, almost more than what we may need. So we're hoping we're gonna be able to downsize that a little bit and still get enough power to operate everything and fit everything.
So right now we're requesting some documentation from Bronco Space. They were a little bit, they didn't have all of their documentation ready to send out currently. So they are putting together a little packet of documentation for us to use. So we will have those answers soon, but we don't have them currently.
changing gears here, 10 minutes to track the ISS, that sounds like you're going horizon to horizon and pretty much optimal paths to the ISS. Have you looked at that practical terms? You know, what was the limit of the tracking station in terms of elevation?
Yeah, so that's actually what we're working on right now. We're doing our link budget, so that will be going into our link budget analysis and some of the other kind of analysis that we're doing on our communication systems. But it hasn't been fully fleshed out quite yet.
You know, one silly comment is that your boom deployer reminded me of tape measures. Press a button.
Yeah.
Yeah. Is there anything to learn from high-end tape measures?
It's actually those were like previous tests were mentioned like way before our time, but it's actually just more like it's like a general demonstration of what to expect, not to. I think the reason they didn't go for is one of those issues. They're like thinking, well, based on the amount of force it probably generated, what if the other, what if like what if you miss the orientation? If you're trying to like mitigate as much risk as possible, that's essentially what it was.
It's not a fine device, right? It just deploys and reels up. It sure looked like a tape reel.
Yeah.
There's been tape reels that have gone to space.
Yeah, I can see that.
Yeah, it is. Like
Cheap solution to this
Yep.
problem.
I think the idea with the current choice to go with the deployer inherited from CubeSat is that there's a mechanism inside of the thing that kind of rolls out the spool that has electrical contacts.
Yeah.
So
slippery.
basically, like if you want to power something on the end of the boom, then you kind of need that mechanism that will rotate as it rotates out and like keep it all organized. So I think kind of iterating on that and figuring out how you're going to power the camera out of the boom means that, yeah, the idea is to like, you know, release it and it'll go and not have it actively driven with a stepper motor, as Ryan said, but you know, incorporating some of our heritage with that and then applying it for this mission is kind of the course that students I think are doing now.
I still go for Springs. If anybody, that all sounds cool, and I'm sure it would work, but Springs never let you down.
Any other questions?
back of my mind, you guys thought of the commercial applications of this? People taking selfies of themselves.
Oh, yeah.
in space.
I mean, I could comment on that since this is, so this is like, more of like a heritage thing, that I don't think we really communicated with, the old leadership communicated with you guys, but, yeah, we were originally intending to open it up to the community. And basically, whoever wants to put an image on the spacecraft, you upload an image, obviously. I don't think we could completely open it up because you'd have to do like content moderation and stuff like that, making sure that there aren't like inappropriate photos going up on the spacecraft. So we'd probably just, reach out to like Space APT faculty or, to the Virginia Tech community. And then we would hand select those photos and then uplink and downlink them from the spacecraft. But yeah, no, that was a serious commercial application because, people pay money to like get a star named after them. It's really just like a sheet of paper that they get in the mail. So hence, making space local, which is, the big slogan of this team.
There's something there to help with your crowdfunding.
Yeah.
Get yourself in the queue for the selfie.
Oh, yeah. Oh, yeah, we were looking into
Yeah,
that.
to be honest with people until,
Yeah.
nothing might be that nothing comes of this, but that's part of the fun.
Yeah, exactly. I think we were also trying to work out corporate deals. We're like, hey, you want your logo to actually be in space? Maybe help us pay for some of the spacecraft, and then we can make that happen. So yeah, so that was sort of like the commercial application that we were looking at. But yeah, I mean, a major outcome is really testing that screen technology, because as the team noted, right, there's a lot of applications for that technology, both on the industry side and the academic side.
Any other last bit of comments or questions? And I don't think I've seen anything come up on the chat or. We're all good, so. Well, again, round of applause for the team here. Thank you for joining us. I think we're looking forward to seeing maybe a future seminar and any updates that you guys have maybe in the next year. Certainly when it gets launched and any results and whatnot after. But with that, I'll close out for the seminar for today and for the semester. So thanks everybody and have a good end of the semester and good luck to all the students. Thanks.
Thank you for having us. Yeah,
Good job, guys.